Hello, today we're finishing off section 2 of module 6. That's the second HSE module, and this one is about parallel current carrying wires, which itself is a bit of a mouthful, parallel current carrying wires, so we need to know what that means. A current carrying wire is a wire that carries current. So we have a wire, inside the wire will be electrons that are moving in a certain direction, and that would mean that the overall current is moving in the other direction, because remember, current is the direction of positive charge. This is current I. Now this is a current carrying wire. We want parallel current carrying wires. So we want a situation where there are two of these wires and they're parallel to each other, at least for a certain length. And for the second one, the current could be going in either direction. It could be going to the right or the left. And we want to know what impact they have on each other. What is the interaction between them? And we're going to do an investigation to demonstrate it. But first, I just want to give you a heads up on what that interaction actually is. They are going to put a force on each other, and it's because of their magnetic fields. We can work out the direction of magnetic fields using the right-hand grip rule. This is where the thumb is the direction of current and the fingers are the direction of magnetic field, just like the right-hand push rule. But in this case, when we've got the current moving in a certain direction, the fingers actually curl because the magnetic field is going to be curling around that current, around that wire. So for example, for this wire here, let's say we were looking at it front on, we were over here, this is an eye looking at it from the top down. So we're seeing this circle of the wire here, over here. The current's coming towards us, so we demonstrate that by putting a dot there for the current. And the magnetic field, if I use the right-hand grip rule, I've got thumb pointing towards me because the current's pointing out of the screen towards you, fingers curling around, and so I see that my fingers curl around in this direction. So I've got magnetic fields that go around in that direction. Looking at this side on one, current's going to the left, my fingers curl around. My fingers are going to go over the top of the wire, around the back and towards me on the front. So it's towards me underneath here. So I draw dots for the magnetic field towards me here, and over the top it's going away from me. Boom, like so. So this is the same drawing just from two different perspectives. Now, we all learn that opposites attract, which is true. But in this case, things work out a bit strangely because you would think if opposites attract, then two currents going in opposite directions, let's say one current is to the left and this one down here, oops, is to the right, you would think that they should attract. But it's the magnetic fields that attract or don't. So if I work out the magnetic field for this one down here, thumb going in the direction of current, I can see my fingers underneath are going to curl under into the page and out of the page on the top. So out of the page on the top, that means the top's coming out towards me, and into the page down the bottom away from me. So we say opposites attract, but the magnetic field where these two wires are close to each other are in the same direction and they're going to repel. So these two wires are actually going to push against each other. It's going to be a force, which I will do in blue. It's going to be a force upwards here and downwards here. And because of Newton's third law, these forces are going to be equal and opposite, no matter what amounts of current or mass or anything that these wires have. Okay, now we just have to do an investigation to work this out. So what we can do is this bottom wire here, we can put that onto a scale which is going to measure the mass of the wire in kilograms. Right, so it's going to give you some number of kilograms for the mass of this wire. And this wire will need to be attached to a power source of some kind. Power source, and in there as well, you're going to want to have an ammeter so you know exactly how much current you've got going in there as well. Okay, ammeter, power source, I recommend chucking a switch in as well, because otherwise this is a very short circuit and it's not going to run for very long at all. There we go. switch, ammeter, power source, boom. So we get a certain amount of amps going through this wire, certain number of mass pulling down. That mass is the force. And what we do for this top wire here, the top wire we also connect to a power source and to a ammeter and switch, which I'll draw in here. Switch and ammeter. You can connect them both to the same power source. Just be careful if it's with the same power. Oh, do I have my currents going the right direction? I don't, do I? This one has to be longer than that one. Yeah, you've got to make sure that your currents are going in the right direction when you're setting this up. I mean, you don't have to, but it's good to be prepared beforehand. I want this to be the larger one, that to be the shorter one. Good, because the larger one is positive and the current goes away from positive. So to keep the arrows in the correct direction, away from positive into negative, there we go. What you do is you see how much mass they have. When you turn both switches on, you then see what the change in mass is. And because it's being forced down by this interaction here, you should expect to get an increase in mass of a certain amount. And the difference in mass is what you care about. You don't care about the overall mass. Obviously, actually, it's not mass, it's changing its weight. So you want to know the difference in weight. Let's say your difference in weight is, let's say they give you a difference of 0.1 kilograms. To work out what that is in weight instead of mass, you need to times it by 9.8 to get the weight. That weight is the force put on this bottom wire. You need to do two other measurements in order to see exactly how this interaction is working, because you also care about the distance between the wires and the length of the wires. So that's distance and the length of the wires which are parallel to each other. So only this part of the wire matters. All the wire up here does not really matter very much because they're not part of this parallel system. So this is L length, and this one I should call R because it's called R in the equation now. The radius, I guess, between the two wires. Okay, once you've worked all those out, you can see then if this equation holds true. This is a constant which is in your data sheet. I1 and I2 are going to be the two measurements on your ammeters. 2 pi is just 2 pi. We've done I1, I2. R is the distance between your wires. L is going to be the length of wire that's parallel to each other. And finally, force is going to be the change in mass times 9.8 that you measured down here. There you go, there's your investigation, and that's also the equation that describes the interaction between two parallel current carrying wires. The only thing left to do is to look at the relationship between the SI definition of an ampere and Newton's third law of motion. And it's really funny. Very recently, we used to define an amp based on this force, that an amp was the amount of current it took to create a certain amount of force based on this law. Okay, and that force was obeying Newton's third law of motion, because there'd be a force in one direction and a force in the other wire, equal and opposite forces. However, 1 week ago, we actually changed the definition of an amp. I know this syllabus has only been out and in use for less than a year, but 1 week ago, the definition of an amp has changed. Now it's based on the amount of charge per second that passes a point, an exact amount of charge. And so I don't think there is a relationship between the SI definition of an amp and Newton's third law of motion anymore. But it's important, I guess it's useful for you to know how both of them work. So the old definition used to be 1 amp is the exact amount of current to get a certain amount of force, and the new definition is an amp is the exact amount of current that gets you this amount of charge per second. So used to be based on the amount of force, now it's based on the amount of charge, and the amount of force came from Newton's third law of motion. The equal and opposite forces here and here, they should be equal in size. That's it.